Okay, well, welcome everyone. It's 11 o'clock by my atomic clock here. So welcome to the Wednesday seminar. We have a special guest today. It's Skip Rochefort from the College of Engineering, Chemical, Biological, and Ecological Engineering Department. No, school. Well, I get it mixed up.
School of Chemical.
School of CBEE.
That's
okay.
Right.
Where he's an associate professor of chemical engineering. And Skip has lots of accolades. He has a degree in chemical engineering from the University of Massachusetts, master's from Northwestern, PhD, and another master's from UC San Diego. No, PhD from UC San Diego. He was an NSF postdoc fellow in France with Degenis, who won the Nobel Prize in Physics in 1991. And then he was also a research assistant at UC Santa Barbara with another Nobel Prize winner, Alan Hager. He's worked for Dow Chemical, Kodak, and at Bell Labs, which is a very famous research center that no longer exists. And or maybe it exists, but it's not. It's nothing like it used to be. He's been here at OSU since 1993, and so while he's a very smart fellow and does a good job when he does research, in my opinion, Skip's main love is teaching, and he has actually instigated or initiated, I should say, some different programs for recruiting underserved minorities, and the Saturday Academy. He's a honors college eminent professor. He's a fellow of the American Institute of Chemical Engineers, and on and on. So one of his recent research thrusts is to, especially since China has stopped taking our recycled plastics, Skip's been developing a low-cost, portable device to turn plastics into fuel, and he's going to discuss that. So there you go, Skip, take it away.
All right. Thanks, John. Well, I don't really have to say anything anymore. John gave you the punchline, so that's pretty much all there is to it. But maybe I'll try to fill you in a little bit. Thanks a lot for that intro. I do want to correct one thing, though. But even though he's dead, Pierre-Gilles de Gennes would not like the way you pronounced his name, and he would have let you know that, John. So let me share my screen here. And I have a few of my students that are here, and in particular, one of them is going to help me with part of this presentation. I can't see the chat from here, but if you want to say something, I think all of you are unmuted, so I don't mind you interrupting me. Okay, so please feel free to do that if you like. I can take it. So the title of my talk is Powered by Plastics, Plastics to Fuel. And I just want to acknowledge our team, because it's really our team that is, the big thing here and makes this whole work. So myself and Dr. Kostas Goulas are both in the School of CBE, and we joined forces about 1.5 years ago to attack this problem in a number of different ways. Kostas does mostly fundamental catalysis work, and that's another part of the stuff that we're doing here. But I'm going to talk mostly today about our practical application, okay? My research team is outstanding, and it's all undergraduates. Well, Merit just became a graduate student, but the amazing thing is this work has been done pretty much all by undergraduates and pretty much with very little funding, okay? So Aaron Nibbler, I just want to, he graduated, but I just want to shout him out because he was the one that bugged me to build this small reactor until he did, and he built it at home in his garage, not his garage, his shed, I guess, or what do you call that? Barn, in his barn, okay? Merit Barber has been leading the charge, and Sasha Kosak is going to talk with us a little bit today, but that team has been amazing. In addition to that, this past year, we added 6 URSA engaged first-year students and second-year students. I guess they're all first-year students, and actually 1 high school student. And then I want to also recognize our non-OSU partners, in particular Ocean Plastics Recovery Project and SCART Falling. SCART has been a tremendous advocate for helping us to find funding. And just yesterday, we submitted another proposal to try to get some funding for this work. And so he's been just a great advocate and a great person in industry. He actually has an industry position in a consulting firm to bounce ideas off of. And then I'm lucky to work with a couple of captains, Captain Andy Schroeder and Captain Homer from Kodiak, Alaska and Santa Cruz. And the connection with them is eventually we want to be able to run ocean plastics in here. And of course, that's another funding source, right? If you say ocean plastics, it opens up a whole other bit of funding for you. So anyway, I want to thank all of those people. And I wanted to do that up front before I get going on this. Okay, so here we go. See if this actually moves. Should have moved. Why is it not moving? Moved before, right, John? Okay, so it doesn't seem to be shifting for some reason. Let's see. I can't get it to go to the next slide, although I did a little while ago. Now I seem to be locked up. Okay, well, I can't get it to move.
Touch the screen, perhaps.
Touch the screen?
Yeah, and now try to move.
Okay. Oh, why did you even think of doing that? I don't understand. Okay.
I don't know. It's magic.
Yeah. Okay. All right. Good. Well, I'll take thank you, Nick. I'll take my laser pointer. Okay. So the plastics crisis, and I don't need to tell you too much about this. There's a whole bunch of data out there. Data comes out every week, but I think the biggest thing that comes out of this is that, as John said, when China closed their borders in February of, I think, 2018, then people started to get worried because we'd been just dumping our crap on them for many, many years. And even, I don't know if you know it, but most of the plastics that were accumulated in Oregon were brought up to Portland and shipped to China on a boat. Okay, so that went on for many, many, many years. Okay, so there's a lot of issues there with plastics in the environment, and I don't think with this audience I need to highlight that too much. Here's one of the biggest tragedies, I think, right here. What I call it one of the real tragedies is that you look around the world, there's kids playing in dumps. This is their playground, and this guy's actually working, right? He's collecting plastics for his family. So this is one of the great tragedies, which we in this country don't see very much, but is really prevalent in a lot of the third world countries, okay? And so I wanted to put a couple of pictures in there. Imagine that this is your 9-year-old kid, and this is where her swing is in this playground with the smoldering pile in the background. And these guys basically, these landfills, as you know, just sort of self-combust, and this smoke comes out. And so this is her playground. And that's the tragedy, right? We don't want our kids, any kids, playing in these playgrounds. So then I think it's important for us to remember that because, you know, in Corvallis here, we don't see that. There's a whole bunch of numbers around, okay, but basically if you said to somebody only about 10% of the plastics actually get recycled, then that's a worldwide, I think that's a pretty good number, okay? Which means that 90% of these things just don't go anywhere, they go into landfills or get burned, okay? So when they went to China, we didn't know what happened to them. They could have been burned for fuel because they were at that time, they were fuel hungry, okay? But anyway, not many of them get recycled. The bigger issue down here is that rural and island communities, of which there are many out there, have limited space. Okay, and guess what? If they're an island, then a lot of this ocean plastic ends up on their shores, and so they end up with a lot of plastic and nothing to do with it. So just as an example, on Kodiak Island in Alaska, where we work with Captain Andy Schroeder, he actually has NSF funding to go out and collect ocean plastics. But the problem is when he brings them in, or when he collects them from the beach around Kodiak Island, they will not allow him to put it in the landfill because the landfill is for the community, okay, the trash generated by the community, not the trash generated by the world. And so he basically puts these in these 40-foot containers, and and it's just sitting there. You can't do anything with it. Okay, so that was kind of the genesis of some of this project, is that we wanted to be able to help these communities that have a lot of plastic waste and have nothing to do with it. And I just want to just sort of say here at the outset, Lek and I had a project years ago with a guy named Will Vinton, who was wanting to use plastics, recycle plastics as building insulation. And that project kind of folded, and Will Vinton unfortunately passed away a couple years ago. But, you know, that was, we've been talking about ways to do this for a long time, and to use these plastics, okay? And so this is just the latest wave of that. I want to sort of say that this is not unique, and I said that in the abstract, right? I first learned about this in 1993. Where there was a company called Conrad Industries in Chehalis, Washington, and they were doing this, and that's right when I came to OSU, and I was really, really excited. I contacted those guys. We had some correspondence. I thought this was a great idea. I looked into it, and then all of a sudden, boom, it was gone. And it didn't exist anymore, and the people scattered. And so it was sort of heartbreaking, but the reason was more political than anything else. It wasn't technological, okay? And so a lot of times what we need to realize is that there are not technological issues. We can do a lot of cool things, right? It's political or economic, okay? So many years ago, well, actually probably around 2008 or so, some people that were working at that plant, in particular Kevin DeWitt, started a company called Plastifuel. And at that time, when I talked to Kevin, a couple of things were really cool. I used to go up there and talk with him. And what he told me was he had finally done the calculations to show what the energy ratio is, how much energy you put into the process and how much energy you could get out. And if it was pure HDPE material, his number was 8 energy units out for 1 energy unit in. If it was a mixed stream, it would drop down to something like 4 or so. But the point was you were getting energy out of it. And so that really buoyed my interest. And Kevin went on to take Plastifuel, was bought by Waste Management, and now it's Agilix Corporation. So Agilix still exists, and you know, they have hard times because Kevin also told me at that time that for this system to be profitable, if you just want to make money, oil has to be about $100 per barrel. And if you've seen the oil prices lately, I don't understand how it can go negative, but I think that means they're not making any money on it. So the oil prices have just tanked, right? And so I think this is going to put a damper on some of the companies doing this, unless we have some regulations that say you need to do it. Okay, so right now, since 2018, when China closed its borders and shortly thereafter, basically the United States, and in fact, every country in Europe, every developed country is constipated with plastics. And I think I like that word constipated because it really explains the situation. We have no idea what to do with the plastics, and pretty soon we're just going to blow up, okay? And so a lot of companies have started to look at plastics to fuel facilities, all right? And that's, and there are a couple that, you know, if you're interested, I can tell you about a couple, but I don't want to focus on that. Agilix is one. There's another one that out of MIT that's doing a lot of work, which is called Renewology. But there are many out there, okay? All right, so what was our mission? Okay, wait a minute, I just got to fix something here. I can't see part of my, there we go. So our goal was to develop an inexpensive open source reactor with simple operation and minimal maintenance. So I wasn't going for the big projects, you know, the 1 million ton things. What I wanted to do is to give people like Captain Andy, who's on an island, who has nothing to do with this plastics, the ability to take that plastic, put it in a reactor of whatever size he needed for the capacity that he had, and turn that into a fuel. Diesel fuel, which he can use in his boats. So he runs 4 boats. Okay, there's other places that have tractors and things like that. That was the goal of this. And honestly, the stimulus for me to start up with this again about 2 years ago came from a woman in Eugene called Helen Liu. And Helen is a very persistent young woman, okay? She's an artist, and she said, I want to do this and have one in my community. I want to put it down the street. And so at first I thought she was a little bit of a wacko, but anyway, she's very persistent. And anyway, she's been a great advocate for our program. She basically kickstarted me into looking at this again. So I do want to recognize her. And I do want to recognize Scott Falling, Titus Recycling, and the Ocean Network. Okay, so a lot of people pushed us this way, even though it'd been something that I was very interested in for quite a long time. Okay, so what's pyrolysis? Well, pyrolysis is different than burning. Okay, so with burning we add oxygen. With pyrolysis, we thermally degrade the molecules. So we take something like a very large molecule like polyethylene, we heat it up to some temperatures, okay, and then we break it apart and we get some smaller molecules. So that's an octane on the right-hand side. So if you look here, here's what polyethylene looks like, and this can be a molecular weight of 250, 300,000 down to some smaller molecule. Now, what we're shooting for in our system is diesel fuel, and we'll show you some of the distribution of the carbon numbers that we get for that product. But anyway, that's our goal, okay, is to take this product and turn it into something which is usable. Now, I will say, and as a side here, we are pursuing some other projects where we do gasification. That's what's called gasification, and use catalysis to come to actually very specific products. And that's the work that Kostas Goulas is looking at. And some of his grad students have also started to look at PVC, polyvinyl chloride, which is not a nice polymer to degrade because you have chlorine coming off, but he's also started to look at ways of dechlorinating that and then using it to turn that into a fuel. So there's some pretty exciting things going on and some novel processing going on also. But today I'm just going to talk about where we are with this, what I would call the small scale reactor. Okay. All right, so what do we do? Well, so far, what we want to do is we want to take plastic. So we have a whole bunch of HDPE virgin plastic like this here, and we've been using that to sort of dial in the parameters for doing the pyrolysis. But here's the plastic, and then you can see we come up with something that that is very close to diesel, and I will show you some data on this later. Now, here's the thing about this. My goal in designing this was I didn't want to do a post-processing at all. I didn't want to do a distillation, even though my students keep wanting to do that. I wanted to have this such that you have this reactor on the ground, you stick your plastic in it, you put your little container on the outside, and you get diesel, which you then pour into your tractor or boat or whatever. Okay, so that lots of people have been saying, Skip, you should do this and you should do that to refine the product. And yes, we could do that. But I want you to keep in mind what our goal is simplicity and a DIY kind of product, which hopefully anybody in any country could put together themselves, okay? So anyway, that's kind of the goal. Here on the right-hand side here is our picture of the reactor that Aaron built, okay? And so there's the reactor. It's a small-scale reactor in the hood in Gleason Hall. And here's our condenser. And so here's a schematic of it. And so what we have is basically we have a bed that's like a 3 or 4 inch pipe, okay, with a couple of flanges on it. We built this thing for about $2,100 total, including all of the instrumentation and heater bands and stuff like that. Now, I do want to mention, so here's the reactor right here, and then there's the condenser, and here's some of the product that we get out. So basically, we collect it in here as a function of time and temperature, and then we put it in little vials. These guys collect it every 5 minutes or something like that. And then this is the product that we get, okay? So all we're doing is taking this, vaporizing it, and condensing it. Now, what happens? Well, we lose some of the low molecular weight stuff out through the hood, and we're working on being able to recycle that. But in a system, in the real world, you could recycle those and then use that as a burner. So we could run this with a burner system down here rather than with electricity. So it depends what's available, but you could just imagine designing this such that once you kick it off with a little bit of electricity, which might be available through solar panels, and then once it's going and it gets going pretty well, then you can take the gases that come off, recycle them. Oops, what did I do? Sorry, wrong. What happened here? sorry, recycle them, and then use that to heat the reactor. So we are, really in phase one of this, just trying to get it out. And so what do we spend our time doing? Well, we spend our time trying to figure out what operating conditions give us the best results, okay? And so the only things we change, right now we've been keeping the feedstock pretty clean, and we changed the catalyst. We use a very small amount of a catalyst that is very inexpensive, okay? Again,
So,
we want to...
may I ask a
Yeah,
question?
sure. Like that.
So the greatest problem with recycling plastic is the diversity of the source, and then all kind of nasty stuff that goes in, colorants and modifiers and all of. Is this part of the research as well?
Sure.
Or are you dealing with divergent plastics?
No. Obviously, so again, I'm just showing you sort of the beginning phase of the sort of the virgin stuff. But when you put, and that's really obviously the ultimate goal, right? I mean, they just, they pick this up on the beach and they throw it in there. So we've got stacks of ocean plastics sitting in our lab, and a whole bunch of other types of plastics, which we're going to work on. And we have worked on it. And what happens if colorants are not a big deal, plasticizers are not a big deal because they go off, they burn off pretty easily. Things like glass fiber and other stuff like that will fall out in the solids content. So at the end of this thing, we have some residual down here, right? And that residual is either charred material or some of the inorganics or whatever, which, you have to deal with. And so I think the beauty of the project overall is that, except for PVC, which is a little bit of a problem because chlorine gas can kill people, right? The other plastics, we can put all of them in there, and whatever you're talking about will come out down the bottom here, which we'll need to clean out, but we can still gasify them. Now, here's the thing. Why would you want to gasify PETE? It's really not a good thing to do that. So the idea would be that you could separate out your PETE if you're in this country, right? And then do something else with it. But if you did it, you can still do it. You can still gasify it or pyrolyze it. And so, and all that happens is that your energy ratio gets a little bit worse. But if you're not worried about your energy ratio, if you're just worried about cleaning the plastic waste, the beauty of this is that you don't have to be making money. So the interesting thing about the small scale community systems is they're not revenue focused. They're very much cleanup focused. And so as long as you can clean up the mess and get something out and not hurt anybody, not be toxic or whatever, then that's the goal of the local sort of what I call community recycling systems that we're focused on. So we have very different motives than the large companies, okay? The large companies want to be able to produce large amounts of fuel, whatever that is, whether it's jet fuel or diesel or oil, and make money. And that's why they want to be big. So I didn't want to get into to that market. What I want to do is I wanted to help local people. And so ocean plastics have other issues, right? They have a concentration sometimes of toxins. They have salt, all of these things. Will that affect our efficiency? Yeah, it's going to affect our efficiency. But do we care? Well, no, because we got to get rid of the plastics. And if we get anything out, whatever comes out this spigot is free stuff. Okay, so waste goes in there, it's polluting my beach, and over here we get something and it's free and I can use it. And the only thing I really want to do is make sure I don't hurt anybody in between. So I think that's kind of what we're focused on, Lek. But right now, in setting up the optimum conditions, we've been looking primarily at virgin plastics. You got to walk before you can run on these things. However, we have run mixed plastics, and we don't get as nice a product, but we still get some product out. Okay, so and we haven't done a lot of that yet. Does that answer your question? Okay.
Yes, thank you very much. Yes.
Yep. But that's a really good point you made. The ultimate goal here is no sorting. Throw it in there and off you go. Okay, and I think that's a reasonable goal if you're not worried about money. Okay. Okay, so So here is some data. So the other thing we've done, okay, is we do these runs, and then we get our product and we take it out as a function of time, and then we've developed a analysis technique using GCFID with a MATLAB script that Sasha will talk about here in a second. And the great thing about this is that we can run it in the morning. Sasha takes it over, or somebody takes it over and runs the GCFID in the afternoon, and then we get our results and we can change our parameters and run it again the next day. Now, of course, we can't do this now. This all came to a halt, but we were really cranking out these data sets and being able to look at a lot of different parameters when we were running full steam. So when we had those dozen people working, we would run in shifts and be able to get this done pretty efficiently. So Sasha, do you want to talk about these plots here?
Yeah, sure. So first, really quick, I wanted to say that there's a reason we chose to produce diesel fuel as opposed to standard gasoline or something. The standards for diesel engines are a lot more loose than they are for sparked combustion engines. So you can see this bottom right plot here gives us a general idea of what the hydrocarbon distribution is for diesel fuel. We used some analytical standards and put together a MATLAB script that would let us take GCFID data and then produce these really similar plots that you can see on the left.
Hey, Sasha, let me just cut in for a second. So here he's plotting mole percent as a function of carbon number, if you can't see it very well. And it goes from 7 to about 20, well, right down here is 27, 28. So this, you can see the primo spot for diesel is right there, okay? The other thing about diesel that Sasha mentioned is if you go to farm diesel, there's even less restrictions. And if you go to boats, I don't think anybody cares. So, so that's another big reason to go to that kind of a product. All right, sorry, Sasha, go ahead.
Oh, you're good. So in addition to that, another one of the things with the fillers and plasticizers and whatnot is you can see on the bottom right plot, there's wiggle room, I guess, for other compounds apart from just simple N-alkanes. You can have oxygenated compounds, and that ASTM tests show that you can have some sulfur content in your diesel, which really isn't even a risk with plastics for the most part.
Well, that's a good point. Let me just add one thing there about that. When we put in some proposals to DEQ in Oregon, Oregon DEQ, sorry, Oregon is really against diesel because of the particulates and things that are released. But when you get diesel out of plastics, it's really clean. It burns really clean. And so that was a plus also. So thanks for bringing that up, Sasha.
Right. So if you want to go to the next slide.
Okay. Are you going to mention the catalyst that we used?
Yeah, that'll be on the next slide.
Okay. All right. Oh, yeah.
Yeah. So we've got a lot of data here, and this is just a few of the important parameters that we started covering. So I'll start with the catalyst type that Skip mentioned. We started with, let's see, we tried iron oxide, I think, and didn't really get good results. And that isn't even one of these parameters here. But we did uncatalyzed. We tried nickel-doped silica alumina, and then there were some papers talking about bentonite clay, and that's actually catalyst C down there. You see it's not very active. So you can see which one we likely went with. Catalyst B there is the silica alumina.
Excuse me, may I have a question?
Sure.
Could you explain the graphs for us, for non-chemists? What do we have on the x-axis? The letters are pretty small, so it's difficult to read.
Sure.
And we have on the y-axis, and what is good, what is bad when we look at them.
Right. Okay. So the x-axis is a carbon number, so it's the number of carbon atoms within a carbon chain. So there's like on the far left there's pentane, number 5, and then it keeps going up until you've got carbon number 25, carbon number 30. And then if we look at the previous slide, there was that carbon distribution of standard diesel fuel. And our goal is really to match that in terms of the carbon number.
Yeah. So if you look at that, standard diesel fuel goes from about carbon number 7 to, well, somewhere around 21, 22, 23, somewhere in there. So that's kind of our goal.
Thank you.
Right.
And then on the x-axis is either mass or mole percent over here. So amount of material that comes out at that particular carbon number.
Great, thank you.
Okay.
Right.
Yeah. Thanks.
There are a couple things that our method can't analyze. This is really just showing carbon number, but it's not showing the degrees of saturation of our hydrocarbon chains. That's something that we'll have to look into a little bit further. But let's see, what else we worked on? Condenser control. So we started out with forced water through a double pipe heat exchanger as a way to cool our product stream. And then kept moving forward with that passive water cooling, which was basically just having the water sit in our condenser tube and letting it naturally convect with the flowing hydrocarbon vapors. We have landed more on passive air cooling, where we simplified down to just a copper tube with natural convection as a way to remove our shorter hydrocarbons. So with the active water cooling, there was a risk of condensing carbon number 6, which we want relatively low amounts of in our product. And, we found with passive air cooling, we could reduce those pentane, hexane hydrocarbons. Temperature control. So this gets a little bit complicated because different polymers are going to thermally degrade at different temperatures. This set of graphs here is for high density polyethylene, and that's going to be different for PETP or polypropylene and whatnot. But
Sasha, can you say when you say that number, that temperature, where is that temperature being measured? Are you going to mention that?
Yeah, sure. So that temperature is in the base of the reactor, which there should be a diagram on one of the next few slides to depict that. So yeah, that's the actual temperature of the main reactor component. So we're getting our hydrocarbons up to 400 to 450 C before they are pyrolyzing and producing a product that we want. In addition to that, there's some other reactor sections where we have to control temperature, and you can see on the far right there's reflux control, where we have our hydrocarbon vapors condensing in a top section of the reactor, and we're using that as a way of separating out heavier hydrocarbons by letting those condense and then reflux back into the main reactor section so that it can further break down into the desirable number of hydrocarbons.
Yeah. So maybe we should go, let's see, is there a picture of the reactor over here? No, that's okay. Let's go back. I just want to show you that. So let's see what he was talking about. So here is where we measure the temperature down in here. Okay, so that's in this part of the reactor. And then over here is where we pack this with, say, the glass wool or the burr saddles, which I think we're settled on the burr saddles now, right, Sasha?
I think we're doing the Russian rings.
Oh, yeah, that's what I meant, Russian rings. Yeah, okay. So we pack this with Russian rings. And that's to actually, there's a couple of different things going on here. One of them is we need to control residence time in the reactor. And so by putting a little bit more resistance up in here, so this can be empty, this part up here can be empty. We can heat it or not heat it, so it has separate temperature control. But when we put the packed column in there, I mean the packed bed of Russian rings in there, it slows it down a little bit and gives it a little bit more time to react. So that helps us. So we can control some of the residence time by doing this. And then this condenser is the one he's talking about, where we can run it either with water running, with water not running, which means the water heats up as a function of time, or with water on the outside does, or air. And I guess we've now settled with air. And again, it's all a trade-off as to how much is going off, how much of the light hydrocarbons are going off, how many you're condensing into your diesel. Because remember, the diesel, what's it, Shastra, we want from C7, say, to C25 or something like that?
Yeah, pretty much.
Yeah, so C7 to C25. So we don't want, methanes, ethanes, propanes in there, okay? And so that's really what we're trying to do with our work, is try to find the conditions that we can optimize to get a reasonable diesel product. So going back to this data, that's what all of, in Lex's question, that's what all the work that we've been doing so far, primarily to try to get to some operating optimum conditions. And we were getting ready to move to mixed plastic streams, and we've run a few of those, right, Sasha? Haven't we?
Yeah, we have.
Yeah, and we don't get quite as nice a product out, I don't think. And sometimes we didn't really show you, but sometimes we also get waxes out rather than liquid. So if you go back again over here. See, there's a little waxy product there in the background. So now it turns out chemical companies actually like the waxy product. So if we were trying to do something and give it to a chemical company, they actually like this because then they can convert it into more different things. But again, remember our goal, right? Our goal is to be able to give somebody this stuff here and let them put it in their equipment. Okay. All right. Is that good, Sasha? We good on this?
Yeah.
Okay.
I think so.
All right. So I want to move on. So that was all done with what we call our bench scale reactor, that little guy I just showed you. Clean Oceans International, a couple of years ago, I contacted them, and they had purchased this particular reactor, which is a lot larger, and it's also a flow-through reactor. So I contacted him because the person who had bought it, who was running it, left, and so it was sitting idle. And somehow Scott Farling actually put me in touch with them and said, hey, these guys have a reactor. And I was thinking of purchasing one of these, but I said, well, since they have one, let's see if we can get it. So many conversations, and about a year and a half later, we got it up here, and here it is up now at OSU. So this is what it looks like. So there's the reactor, and then there's the condenser part of the system, I think. Here's what it looks like. So it came up in a trailer. It weighs about 1,100 pounds, this system here. Came up in a trailer. So thanks to the Forest Research Lab folks and the College of the Wood Science and Engineering people and whatever, we were allowed to move this into, I guess we call it Oak Creek West building. I think that's the name for it. And John has a space there where there's a injection molding system and an extruder. So we were able to move it in there after lots of conversations. So this is just a picture of the system right here, and we'll show you a schematic of it, but there's a hopper here, and it's actually a continuous feed system. What we're doing now is dismantling it so we can pull it out. Okay, so again, here's the reactor. So you can see it looks very similar to ours, right? I can't remember if I saw this and then we made ours, or if we made ours and it just turned out to be similar. But anyway, they're very similar, except this guy's basically just ours on a little bit of steroids. Okay, so it's just a little bit bigger. You can process 50 kilograms per day. Ours, we really process about a kilogram every day or half day, something like that. Okay, it's got a continuous feed system up here. It's got a way to deliver catalyst inline. We have somebody who's interested in helping us develop catalyst, and in fact, Kostas is a catalyst expert, so we may be working on developing new catalyst also. But again, for this low cost system, we want to keep to the catalyst we're using because it's very cheap. And then it does have a fractionating condensing unit in it, which is a little bit higher scale. So this is just basically a bump up in terms of technology than the one that we're building for community systems. So this we're gonna work on this one also. Here's a schematic of the system. Okay, so it has basically a screw system here, like a little extruder. You can feed the solids in here, and Then it comes into the reactor, which has various heating zones, and it's also got an external mixer. And then there's a catalyst bed here, and then some fractionating unit here. So it's a small scale commercial system. I think it was designed for, well, for something like 50 kilos per day, so 100 pounds or so per day. And it was available commercially from a company in Michigan. Actually, the company is like one guy, and they only made 2 of them. He has one, and then this is the second one. Okay, so so there's only 2 of these that are around, and we're lucky to have it. So Clean Oceans International and Captain Homer let us borrow this on loan, and so we have it right now. We haven't run it yet because this is, I want to show you, this is called getting it out of the trailer and into the facility. And so we did that, and then successfully moved it in. There's our crew, and you can see on the left-hand side is the injection, the extruder. On the right-hand side is the injection molding machine, John. So we're stuck right in the middle between those two. And it's great to have that facility because it's got a lot of power. It's got the power we need, and also the venting system, which is up over here. There's a venting system too. So here's we were very proud of ourselves because it took a lot to move this. So here's our crew on moving day. You can see the trailer is empty, but we still have a trailer. And so, here's you're outside of Oak Creek West. This is what it looked like, and then now it looks like this because we moved our trailer there. And I don't know if anybody on the call has any authority, but nobody's yelled at us yet about having it there. So this trailer is now sitting right here, and it's empty, essentially, just a bunch of peripherals. So that's where we're at on that facility. And so what do we want to do in the future? Well, obviously we want to move up. So we have 2 things going on. We have the bench scale reactor. We're going to continue to do some work on that. We'll go to mixed plastic streams in there. We need to get the larger system, what are we calling this thing? I can't remember. What are we calling it, Sasha? Do you remember?
The PTFT, or did we change it?
Okay, we call it the PTFT, plastics to fuel in the trailer. So the plastics to fuel in the trailer unit is we need to get that going. We haven't even turned it on yet. I think maybe we heated it up a little bit, so we need to get that going. So and all of this was planned for now and in the summer and whatever, and I'm not sure where we're going to be on that. But we also, as Sasha pointed out, I think we need to look at some fuel standards. ASTM testing for diesel is not cheap. It's about $1,000 per sample, so we haven't been sending it out. But that's something we probably need to do at some point. And then everybody wants to change the design on our bench, the BSRs, the bench scale reactor. Everybody has ideas on how to change this. I have to fight them and try to keep it simple. But I'm quite certain that if we had to right now, I think we could build one of these things and give it to somebody. And so Captain Andy, in this pandemic, Captain Andy's been kind of, his boats have been basically in dock, and so he has all this plastic, and he's kind of in a hurry to get one of these units up there and be able to test it out. So we're thinking about where we go next with that, and so that redesign. Something which just happened this past week, actually just yesterday, there's a company in Europe that I can't name who's interested in these types of reactors, and we put a proposal into them to be the basically the characterization facility. So we would take we would have a system that we'd run at OSU that would take the waste in, we'd run the conditions, try to get optimum product, and then we would give that information to them for the design of their larger systems. Scott Farling was the lead on that. And the nice thing about that one is that the material we would receive would be the stuff, excuse me, the plastics that are rejected by the MRFs. Okay, so the municipal research, whatever they call those, recycling facilities, MRFs, are sorting plastic still, and certainly if you can sort the plastic and actually use it, like PETE or something like that, that's a good way to go. but they also have a bunch of plastics that they can't use. So that reject plastic from the MRFs would be the stuff that this company would take, is looking to take and turn it into a fuel, okay, because there's still value there. So what they want us to do is we would take that reject material, we would run it, try to optimize some conditions, and then help them with their reactor design. So that's pretty exciting. Again, it all comes down to this last line, money. Okay, we've submitted several applications already. Not everybody, lots of people are interested. Not a lot of people have put their dollars into us yet. But the good thing about constipation is if you don't relieve it, it just gets more painful. And so we just need to wait till we get to the point where it's extremely painful for some people. And I think they'll give us some money to do some development on this. And so that's, I think, probably the same thing. Here's our group. We're at the 2020 Asian Festival. And so to show you how portable our reactor is, we just loaded this into the car and brought it down there and ran it at the Asian Festival and got some reasonable product. Okay, so here's our little setup at the Asian Festival, and there's part of our crew. And so I think this was an important step because we were able to take this reactor here, out of our lab, put it in the car, bring it to Eugene, set it up, and actually run it successfully. We were all pretty happy about that. And it was chilly out, it was raining and stuff, so that's why we're all dressed up there. Here's the references for at least some of the references for this. And then the very last thing I want to do is I want to thank Helen Liu. So this is Helen right here. Okay. And remember I told you how this woman came into my office and said, I want to do this. And I thought she was a little wacko. Well, Helen is a little wacko. She's a wacko in a very nice way. You can see by her smile there, that's how she is. She's very energetic. And she also gave me a little panda. And so this is at the Asian Festival, and that's our crew down there at the Asian Festival. And Helen came in and said, I want to support you. And she gave us the money to actually build that first reactor. And she has continued to support us quarterly with some funding to help pay these guys and give them some food. Okay. And I'm really very thankful for Helen. She's a great supporter. She really is the one that actually got me off my chair and said, okay, you should do this. And so I want to thank her for that. And with that, I'll end up. Looks like we're pretty close to the end anyway, but we can take credits for sure. Questions for sure. And again, I want to just thank my whole team. So I can get out of this, I think. Yeah. And see, okay, oh, there's 11 questions. All right, let's see what the chat looks like. The thing that is most of what you get. Okay, hold on. Let me read some of these questions. Shout out to artists. Yes. Okay. So somebody says shout out to artists, and I gave you the name. Okay. Tiana, thank you. You're welcome. Okay, with a lot of little chat stuff going on here. How do you deal with additives? Okay, I answered that one. Go ahead and unmute and ask. Okay. Sorry, I'm just reading through these things. The thing is that if anybody has something they want to say, go ahead and say it. Yeah, okay.
So this is John, and how are you going to separate the PVC?
Yeah, so
that's going to be a real problem, right?
Yeah, okay, and so you know, that's a good question, John. And on the small scale, I think it's not that hard because if you get something that's sort of very flexible and plasticky, it's either going to be an LDP or a PVC. So you just don't throw it in there. Honestly, I was thinking about, so what they do industrially is they put the chlorine comes off and then you scrub it, right? You can scrub it. And so we've talked about putting a little scrubbing unit on it too, right, Sasha? I think at some point we talked about that.
Yeah, but you're going to be making hydrochloric acid, so you got to be careful about your materials, right?
Well, sure, yeah, but you know, it's going to be weak HCl, right? I mean, yeah, you do have to be careful of your materials, but I mean, it's certainly a question. And you know, the other question is the toxicity. How much PVC is in there, and how much, you know, is not. most of the plastic waste, if you look at ocean plastics, John, and so Sasha and Merritt went on a cruise with Captain Andy, and they spent a week picking up ocean plastics. The majority of the ocean plastics are either HDP, LDP, or polypropylene, and the most of the stuff that comes up on the beaches is that. There's not a lot of PVC that comes up as far as we can tell. But the stuff that does come up, it tends to be smaller microplastic type stuff, and they don't have, there's not a lot of chlorine there. So that's kind of a BS answer, honestly, because I don't really know the real way we're going to have to deal with this, except that I think the majority of the plastic waste that comes from single-use plastics, and most of those are not PVC right now.
Right. Any other questions? So I'll ask another one.
As Skip mentioned earlier, Dr. Goulas has a student working on PVC dechlorination, which would be pretty useful for this project.
Yeah, that would be awesome.
Yeah, that's good, but of course that's a research one, and that's not somebody in Kodiak Island's not going to necessarily run that process because it's not too easy to do. But the oil companies might be interested in it, and in fact they are. So we're partnering with a couple of people right now that I can't mention, but anyway, there's some stuff going on there.
So my next question is, can I bring you my polystyrene peanuts and throw them in your reactor?
So you could, John, but if you were a conscientious recycler, what you would do is you'd compress those guys into a little block, and then the next time you go up towards Portland, you drop them off at Agilix, because now Agilix is almost completely focused on taking polystyrene, styrofoam, exopolysaccharides, exopolystyrene, and converting it into styrene. So they've partnered with a company called Styrenics, and they've gone from mixed plastic streams almost completely right now to just taking styrofoam, and they have a little call out. So I could do it, John, but again, as long as you don't care about the cost, it's fine. We can do it. We don't get a very good product, right, Sasha, out of styrofoam. Have we tried to? I think we've tried to run polystyrene, right?
We did, yeah. We got largely styrene out, which I haven't looked into it too much. But if you could separate that from the rest of the products, that could be valuable.
Yeah.
Yeah, but that's really, you're trying to be non-toxic too, so.
Well, but John, if you give me only styrofoam and all we're running is styrofoam in there, then you change your process a little bit, right? I mean, you collect a different thing.
Yeah.
This is the other John. How do you compress your polystyrene at home?
Well, I weigh a lot, and so I just sit on it. So you can't, John. Okay, and that's an interesting point. So right now, the first alternative, so in Corvallis, the first alternative food co-op takes styrofoam. You give them a little bit of money and they take it. And I've been begging, and honestly, right now what they do is they take that styrofoam, they put it in a truck, and they drive it up to Tigard and drop it off, which is absolutely the craziest thing in the world to do, but I can't convince them that that's the case, okay? There are a couple of companies that are willing to donate basically industrial scale compressors, so you can put them in there and compress it down. I don't know if Lek remembers, but we did some work when Lek and I were working on the building installation. A guy in Kodiak, and not Kodiak, in what's above Canada, whatever up there, really cold Canada. He sent down some stuff that was compressed styrofoam that he wanted to use as building insulation in his house, and we measured the properties, and it was pretty good. And he ended up using it in his house. So you gotta compress it. It's not easy to do at home. You're right. The co-op should work with me to put a compressor, a compressing or system there, and then compress it. The thing they told me is we don't have electricity where we collect the styrofoam, so we can't run it. And it's like, okay, that's crazy. But anyway, people are people.
Yeah.
Yukon. Sorry, it was the Yukon. There it was. This guy came from the Yukon, and he sent me his stuff. Yeah.
Well, and do you have it? Even when you compress it, I was thinking you could put it in the oven and then compress it when it's hot.
Yeah.
But it's going to off-gas pentane, so you might blow up your stove or your house. So.
I didn't recommend that, John. You did.
Okay. Any other questions?
I have a question.
Go ahead.
Hi, Skip.
Hello, Sweater.
My question is, I figured out that you guys have been trying to keep it like a bench scale to keep the, expenses lower so that it can be more useful for, changing these plastics into biodiesel and not for a much larger scale. So when you are applying for like fundings and stuff, so what are the main technical issues you are facing where you want like, more investment or more money to make this process or system better than how it's running now?
Well, yeah, that's a good question. And so every proposal is a little bit different, right? If you write an NSF proposal, they're looking for transformative technologies. And so what we do is we talk about the dechlorination of PVC and put enough money in there that we can pay Sasha to work on the bench scale reactor. But the proposal we just put in last night is one where they want us to have a bench scale system, and we may modify it to meet to be more like theirs. Okay. And so what you need to do is, what we're trying to do is to be able to come up with a really good bench scale system that we could, like I said, DIY or open source, but also, we want to also be doing good research too. So it's kind of a trade-off between the two, and every agency you submit to wants something a little bit different, and then you say, okay, yeah, I can do that. And in the process of doing that, if I pay Sasha to do something or I pay Merit to do something, they can do something else too, right? So I want to keep the community aspect of this alive, but I'm not certainly against money to do further stuff too, right?
Okay.
It's kind of a game. It's a game.
Yeah. Yeah. Thank you.
Yeah.
Is there a final question?
I have a
We're
question.
about out of time. I'm going to unmute everybody if this works. And I don't think it works. But anyway, you can unmute yourself, and let's give a round of applause to Skip and Sasha for a very nice presentation.
Yeah, those little emoji things are cool. I have the students do that for me. The little thumbs and the clapping. Yeah, they're good at that. There we go.
Okay.
Makes you feel good when you see those come up, even if they don't mean it. All right. Thanks a lot. It was fun, and thanks Sasha for sticking in here with me. And nice to see you, Milo. A little black box there. Okay. And Ian Morel, I think Jeff came in as his alter ego as Ian, but I don't know. We'll see.
It's his son.
I know it's his son, but who even really knows? It's a black box.
I don't know who I am either, so it's fine.
All righty. Thanks a lot. Thanks, John. It was fun.
Thanks, everybody. Tune in next week for our next speaker. I'm not quite sure who it's going to be. I haven't got confirmation yet, so I'll let you know as soon as I know. Okay. Take care.
Yep.
Have a good day. Stay safe.